Thank you very much for clicking on this video. In this video, we are going to look into organic chemistry. And here we are going to look into just the introduction of organic chemistry. Here I'll be looking into electron configuration, lone paired, bond paired, unpaired electrons. We are going to look into ground state, excited state of carbon, hybridization, catenation. Then we're going to go for the definition of organic chemistry and discuss organic compounds properties. Therefore, I urge you that you pay good attention and do what I ask you to do in this video. Let's start with electron configuration. What we mean by electron configuration? Electron configuration is the distribution of electrons around the nucleus of an atom, following some certain rules. I know your question will be, why did I start with this electron configuration? Yes, it is very, very important. If you understand what we mean by the word atom, which is the smallest part of an element that can take part in a chemical reaction, and you understand that this atom is made up of subparticles, proton, neutron, electron. Where the proton is positive, neutron has no charge, and these two are found in the nucleus of an atom. And the electron is negatively charged and it is found around the nucleus of an atom. It could be of the shell, it could be of when it is being grouped as orbitals. Therefore, this is very, very important. If you understand these atom properties of an element, atomic properties of an element, it makes it easier for you to understand what you are to study in chemistry. In this organic chemistry, we are going to look into the study of carbon. Therefore, it will be very, very good to look closely to electron configuration of carbon. And I would like you to look into this Albao principle, Horn's-Rule, Pauling exclusive principle. Although I will be making use of them, but I'm not going to discuss much on them. But we are going to look into the electron configuration of carbon, and I'm also going to bring in nitrogen so that you will understand how to do electron configuration using the shell format, which mostly called KLMN format, and the orbital format, which is known as the SPDF format. Therefore, I'm going to introduce carbon and nitrogen. The atomic number of carbon is 6. Atomic number of nitrogen is 7. I know I'm not going to spend much time on Albao principle, Hunt's rule, and Pauling exclusive principle, but we are going to make good use of them in this little exposition on electron configuration of carbon, although I'll be working alongside with nitrogen. And atomic number of carbon is 6. This means that the total number of proton in the nucleus is 6. I hope you got me when I said the subparticles of atoms include proton, neutron, and electron, and I just described them just before now. And that of nitrogen is 7. It means that the total number of proton found in the nucleus of an atom called nitrogen is 7. Now, if we have the total number of protons to be 6 for a neutral atom, it's also going to have the same number for electron. So if we have 7 proton number, we're also going to have 7 electron number, and we define this electron configuration to be the electrons distribution around the nucleus. Therefore, we are going to look at how these electrons are being distributed using the KMN format. I'm going to start with having a table of carbon and nitrogen in order for us to understand this very, very well. So this is carbon, this is nitrogen, and the atomic number of carbon is 6 and that of nitrogen is 7. That means that, as I said earlier, that the number of electrons for carbon is going to be 6. You're going to distribute it around the nucleus of the atom based on energy level and following certain rules. The same thing is going to be done here. But our major focus is on carbon, but it will be good to work alongside with nitrogen so that you will understand how to fill electrons or how to distribute electrons around the nucleus of an atom. So we have, using the KLMN format, that is the shell, the principal quantum number, we will have, if I remove 2 from this 6, it will remain 4. If I remove 2 from this 7, it will remain 5. Hope you get that. Okay, we can actually demonstrate this thing using a diagram. We normally use circle to represent this. It is normal to every chemistry student. You're supposed to have seen that several times. Therefore, let me use this circle pattern too. You have to know that this two circle represents the two shell. Hope you get that. Therefore, we're going to first of all fill the twos in this first shell. This is the K shell. Hope you get that. Okay, let's fill them. If we are using the SPDF, this first two is what we mean by the s orbital. Please, I have a consistent pattern of filling this electron for a purpose. Therefore, this is the s orbital. You are going to understand this the more I go further. Let's fill the L shell. If you look at this, you notice that 1, 2, 3, 4 represent these four, but in here we have 1, 2, 3, 4, 5 representing this. So I have actually done the electron configuration of carbon and nitrogen using the KLMN by writing and by demonstrating it using a diagram. Now let's go for SPDF format. That is the orbital format. We will have something that look like this. Here we are going to fill them one after the other. The maximum number S can contain is 2. And the maximum number P can contain is 6. The maximum number D can contain is 10. The maximum number F can contain is 14. Now let's fill them following the Albau and Horn's rule. If you notice, the L shell 1, 2, 3, 4 is this 2 here. That means that these two represent the second energy level, whereas this one represents the first energy level. And this represents the orbital called s orbital. Another word for it is sharp. It has no magnetic deflection when presented in the midst of a magnetic field. But this P has magnetic deflection. That's why we are having a P here, a P here, a P here, or better use here P, P, P. But here is only S. I don't know if you get me on that. But I'm going to demonstrate it more so that you understand what I mean by having deflection. It's going to be of X axis, Y axis, or Z axis. We go using box. You can notice they have different spin. Watch that. Okay. So this is the electron configuration of carbon and nitrogen. Okay, the atomic number of fluorine is 9 and that of oxygen is 8. I would like you to get this done for oxygen and fluorine for me. Okay, I can break this thing down further to look like this. I hope you can understand this. Now, if we look closely to this diagram, you will notice that this electron is alone, but this electron is in 2. In the last energy level, we have only one of the orbital having 2 electrons in it. These 2 electrons found inside these 2s, or even if we see it in any of the 2p's, we call it lone pair. Lone pairs are those 2 electrons with 2 different spin, as you can see here, in the same orbital of the same atom. And mostly people define it as that non-bonding pair of electron. Yes, but let me tell you, sometimes it can be used in bonding, something in the nature of coordinate bonding or even in metallic bonding. And if you also look very, very close to this, you notice that these ones are alone. These ones that are alone belong to be paired. Look at it naturally. In our real life, every one of us want to mingle. Every one of us long to be paired, coupled. The same thing happens in these electrons. They want to be paired. Now, because they are not paired, we call them unpaired electrons. So we can actually define these unpaired electrons as those electrons that are not in twos. What I mean by in twos, they are not paired and are actually ready to be paired with other electrons. It can be of the same type of atom or from different type of atom, and this is only achieved by bonding. Bond paired electrons are those 2 electrons that are together as a result of bonding. Let me tell you, I said that in the lone paired electron, we can see it in coordinate or metallic bonding. The unpaired electron can actually be used to have metallic bond, we can have ionic bond, we can still have something like covalent bond. But now bond paired electrons are mostly seen in ionic bonding, coordinate bonding, and covalent bonding. So we are going to have a little demonstration only using ammonia and water to explain what we mean by bond pair, lone pair, and unpaired electrons. For ammonia, so let's demonstrate these three hydrogen using the diagram. We will have something that looks like this. This is three hydrogen atoms coming together to bond with one nitrogen atom. If you notice, this is lone paired electrons, but these are unpaired electrons. The total number of unpaired electrons here is 3. Therefore, we have 3 unpaired electrons from hydrogen coming to bond with this. Therefore, each of these hydrogen is going to bond with all this. So we will have, in the aftermath of the reaction, this. If you look at this is blue and black. I hope you get. I purposely use the two colors in order to make it easier for us to understand. This is a bond pair. One of the electrons is coming from a different atom, one of the electrons is coming from another atom. I hope you get that. This is from hydrogen, this is from nitrogen. Therefore, we have it as bond pair. Although we can still have hydrogen coming again to bond with this place, but that is a type of bond we call coordinate bonding. But that is not the major issue of this video. So the information here are 3 bond paired electrons, 1 lone paired electrons for ammonia, and the shape of the molecule is going to be trigonal pyramidal, and the angle is about 107 degree to 108, but mostly we use 107 degree. And for water, we have 2 bond paired electrons. The 2 bond paired electrons are these, and the 2 lone paired electrons, which are these 2 red. As you can see, it is clearly shown. And I asked you to do for hydrogen fluoride and methane for me, and it will be better. But for this water, the shape is V-shape by molecular shape. Angular, some people say it is angular, some people say it is bent, some people say it is non-linear. Any of them you see is correct. I hope you get that. Therefore, do that of hydrogen fluoride and methane for me. Let's continue by looking at the ground state and excited state of electron configuration of carbon. I urge you to make sure that you subscribe to this YouTube channel and click the notification bell to give you alert or notification for updates of my videos. Very interesting videos that help you to get more knowledge in chemistry. And don't forget to share my link and spread my message to people around you. Let's assume that I employed X, Y, and Z to a baking industry, and also employed these 2S. And this guy is working here, this guy is working here, this guy is working here, and this guy is working here. And I'm paying 1, 2, 3 the same amount, just a little bit above this in the same energy level. Okay, and you notice that if you were X or Y, you'll be complaining for this Z. Now the same thing happens in chemistry in the electron configuration of the ground state of carbon. This looks unbalanced. Therefore, for this to be balanced, this electron here needs to be promoted to the Z. Is the promotion of this electron from here to here what we mean by excited state? So in the excited state, there is one of the electron here leaving, going to this. Now, if you are to write the electron configuration of the ground state and the excited state of carbon, they will look different. And this disobeys Auber's principle. Yes, despite it disobeying it, it is still correct. We can see something that looks like that in chromium and copper in their d orbitals, because their number of electrons halfly filled or completely filled is above 60%. Therefore, the long to be complete, let it just be 100. It's above average, greatly above average. That is the reason that they tend to be stable at this position rather than this position. This is what carbon normally used to bond, and not this. So let's write the electronic configuration of the ground state of carbon and excited state using the normal SPDF without this. There are a series of questions they can ask you about this information. If you check your WAEC past question paper, your NECO past question paper, your GCE past question paper, NAPTED, you are going to see so many questions that ask us about the ground state and the excited state of carbon. They even go further to ask us something of the chromium or copper electron configuration. Sometimes they can ask you copper 1, copper 2. I'm going to explain that of copper and chromium when we are treating electron configuration of the transition elements. For now, we are going to look into another thing, which is hybridization. In this hybridization, it can be defined as the joining of more than one orbitals to produce the same number of orbitals but different shapes and better disposed for chemical bonding. Yes, this definition, you might not fully understand this until I put it into demonstration. That is why I'm going to make use of a simple demonstration. But before we go, I want you to recall of this diagram. If we want to represent carbon, because of this statement, if we want to represent carbon is supposed to have 4 unpaired electrons. In chemistry, you will normally see 4 lines going towards carbon in this form. So each carbon is supposed to have 4 lines. Now, because of these 4 lines and also using these 4 lines, I am going to demonstrate something beautiful for us here. Let's look at this. Let's say that this is the 2 carbon we want to bond with. I am going to give the label of this S, P, X, P, Y, and P, Z on this. You know, at the right hand side, we're supposed to have X axis. I don't know if you get this. Okay, let me do the same thing for the other one. Okay, for us to have different spin, let's assume that this is bonding to this. You know, we are now going to make use of 2px and 2s. This is what we are making use of. That means that this also is also going to be made use of. And if you are making use of only 2s and 2px, we are making use of what we call sp orbital. That is, we are bonding with this 2ps against this 2s. We will have something in this nature. Since we are making use of the sp orbital and these two are not to be used in this bonding, this will be waiting for something like another carbon or something like hydrogen to come and bond with. But these two that are not going to be used in bonding, they are going to do what we call overlap, where this will bend down here, this one will bend down here. We will have something that look like, which further, since this one is not also bonding, will also bend in the same form. We will have, this will give us what we call triple bond. And you look at it very, very well, it is linear. Now, because we are using a combination of an S and a P hybrid, that is how we got this. Remember, they say joining of more than one orbitals to produce what? The same number of orbitals. That is what we did here. Now, let's go again with this. Remember that this is what we are using to bond. That is, we are picking 2s and px of a carbon atom to bond. Now, if you are making use of 2s, if you're making use of 2s, 2ps, and 2py, how will it look like? Let's look at it. But before that, know that the angle here is linear. It is really, really linear. We go. Here we are making use of a 2s, 2px, and 2py bonding. That means that we are ignoring the z. That means that these two parts will be the one that is going to overlap with one another. So we will have what look like this in nature. Not perfectly, but it will look like this. Note, when this curve is going to pull this to change its style, it will look like this perfectly. This has only one pi bond. This have 2 pi bond, that is 2 overlaps. This have only one overlap. I hope you get that. And these are the sigma bond. Now let's look at the angle. The angle here is going to be 120 degree. The other one was 180, that is linear. This one is going to be 120 degree. Let's look at the last hybrid. We call this sp2. We call this sp because we're only making use of these two to bond, that is S and PX. That's what we're using. But here we are making use of 2x, 2px, and 2py, ignoring the 2pz. That is what gave us we have 2p we are using and only one s we are using. And you see how the diagram is. Let's look at, if for instance we're making use of all of them, that is 2s, 2px, 2py, 2pz, how will it look like? If we're making use of all of them, you will notice that each of them are still waiting for bonding. Here, this place can be fixed with hydrogen, and this is single bond, this is double bond, whereas this is triple bond. I need you to know that this is sp3 hybrid, and the angle mostly is, and the angle is 109. That is the angle between the two bonds here. It's going to be 109. You can fit in anything there. We are done with the hybridization, and I believe that you can actually explain it. The first one, the sp, will give us a linear shape. The sp2 will give us trigonal planar, and the sp3 will give us tetrahedral. And this existence of carbon bonding with carbon is what we call catenation. And this catenation is said to be an observation found in some elements on their ability to connect their atoms together to form long chains. We can see it in silicon, we can actually see it in carbon, but that of carbon is more strong because carbon has a smaller atom compared to silicon. Therefore, we have it more in carbon. This gave rise to more of carbon compound than silicon, and this gave the attention of chemists to look into organic chemistry, or the study of carbon, which gave the definition of organic chemistry to be the study of carbon compounds excluding metallic carbides, the triisocarbonates, the cyanides, and the oxides of carbon. If we just remove this, the remaining carbon compound is actually what we know as organic compound. This organic compound, how can we identify this organic compound? There are properties that we can use to identify organic compound. They are as follows. So if we have any compound that has the following as its properties, then we can actually say that they are organic compounds. Thank you very much for watching this video to this extent, and I am very happy to have you. Don't forget what I gave you as instruction and what I beg you of to do for me, to make sure you share my link to your friends on your Facebook, your Twitter, your Instagram. Make sure you spread the message, and don't forget to click on the notification bell for updates. And if you have not subscribed, please make sure you subscribe to help me to remain relevant.